All right, good morning. This is a virtual download for Tuesday, December 8th. This is for my B-Day physics classes, guys. Sorry, but I am not going to be in school today. I am going to try and give you some useful information in this video, some stuff to help with those problems from universal law of gravitation, and then some guidance on how to start the lab that's assigned today. All right? I do need you to bear in mind that the assignment and the quiz are still due today for your first try. If you want to wait until you have a chance to talk to me to do your retake on the quiz, that's okay. But part of being in class today is taking the quiz and submitting the assignment for Edgenuity under the universal law of gravitation. Okay? Before you get to that part, because you've done that solo for a lot, let me go back and demo one of the problems from the instructions in determining gravitational force. All right. Now, uh, these kinds of problems are not they're not that different from other physics problems. The one big difference and the one big difficulty that we're going to have to adjust to is that the numbers we're using now are sometimes so big we need them in scientific notation. So I'm going to be writing down the numbers on a piece of paper. It might take half a page. Heck, for a more complicated problem, it might take a whole page. And that's not because there's a million steps. It's because there's just millions and millions of kilograms and millions of meters inside some of these objects that we talked about, or inside some of these distances. But by writing down what we want to do on the paper first, it's going to make it easy to copy that, three or four figures at a time onto a scientific calculator. And I'll show you how to do that. But that's like the last step. The first thing we want to do is just get this organized, right? So you can see the problem I've got up here. Determining gravitational force. A 5.3 times 10 to the 12th, that's 5 million millions, kilogram satellite is 1,800 meters from another satellite that is 3.5 times 10 to the 8th. What is the gravitational force between the satellites? All right. So let me get this other camera going. We're going to have to switch back and forth a little bit, but that's fine. Um, Actually, I'm just going to read it on my other screen, even though it's blocked for your recording. So looking at this and the information here, I'm making a list of what's useful, right? So one of the masses equals 5.3 times 10 to the 12th kg. That's good. We want everything to be in kilograms, meters, newtons, seconds, right? The distance is 1,800 meters. We'll call that M1. M2, the other mass, was 3.5 times 10 to the 8th kilograms. So I'm just keeping track of what variables I have to mess with here. And the thing that they asked for in this problem was the gravitational force. So Fg equals question mark. That's what we're going for. All right. Now, as we cast about in this lesson, there's two equations with an Fg in them. One is the classic Fg equals 9.8 times the mass. But that only works when we have two objects, and one of them is the Earth, and the other object is on the surface of the Earth, which is where we live all the time and what we're used to. However, that is not what's happening in this problem. Remember, this is two satellites that are, and we're talking about the force between them. Okay? So we need to use the universal gravitational equation. Fg equals capital G times m1 times m2, all divided by the distance squared. Get a different pen. This one's acting up. So thankfully, this equation's already arranged so that the variable I want is all by itself on the other side. So the next step is just to start substituting numbers in for where they should go. Okay? So capital G, you should know from the notes, is going to be 6.67 times 10 to the negative 11th. It's always, capital G is always this number. And this is known as the universal gravitational constant, all right? So that's one number. I'm going to put this in parentheses because when I'm moving later, the parentheses are going to help my eyeballs recognize like different numbers. So M1, 5.3 times 10 to the 12th. I'm leaving units out. There's so much writing with this. I'm leaving the units out. I know it's bad practice, but we're focused on calculation right now. And M2 is 3.5 times 10 to the 8th power. So that's the top of this fraction, and then here's the fraction bar. And all of that has d squared underneath the bottom. So I write d, which is 1800 squared. So I need to get all of this into a calculator, right? So I'm going to find a calculator over here. And if you have your own calculator that does scientific notation at home, like that's totally fine. You can do that. However, I'm going to show everybody how to do this on Google Calculator because it's free and it's accessible to everybody. All right. And I'm not sure if the size of the video is big enough, but we're going to go with what we have. So the really important button here is the EXP button. That's the times 10 to the power button. And so let me show you how to, we enter the first number 6.67 EXP, and there's the E. That E stands for 10 to the whatever power comes next. And it's going to be negative 11th power. There's 11. Where do I throw a negative on there? Do I just throw a minus sign? Oh, nope. All right, let's start over. Negative 11. See if that gets us. Okay, I think that makes sense. So let me start going line by line through this equation. 6.67 E minus 11 times 5.3 E 12, the middle term, times 3.5 E8. So again, that E stands for times 10 to the whatever power. This is E12 means times 10 to the 12th power. E8 means times 10 to the 8th power, right? These are just ways of getting scientific notation here. And then all of that is divided by 1800 squared. No square button, but you know what? They have the X to the Y button. 1800 to the second power. All right. Now, when you do this in the future, you're going to want to put this bottom term in parentheses if it's an exponent. So actually, let me go back and show you the proper way to do it. Even though it doesn't help in this example, if you're just looking for the easy mode, do this every time. Put that distance number in the bottom and then x to the y power 2. So checking back on my data, 6.67 times 10 to the 11th, check. 5.3 times 10 to the 12th, check. 3.5 times 10 to the 8th, yup. 1800 squared, yes. All right, I'm ready for the equal sign. My final answer, 38,187.8. Why not? That's the force of gravity. I have no idea if that could even be the right answer. Let's go back to the question and check it out. Oh, there we go. All right, 3.82 times 10 to the 4th. And again, 1, 2, 3, 4. If I'm converting this to scientific notation, 3.8, that 1 gets rounded up to 2 times 10 to the 4th power. And it's newtons. That makes sense. Alrighty? So that's how we do it. Let me get a nice big picture in case you really want to see what's on my paper. Okay. So that's how to use Google Calculator to do your scientific notation calculations. Turn that off now. Moving on. So we've reviewed some concepts. If you need to know a little bit more about how to use Google Calculator, there's that YouTube link. It's the same one that was posted in the classroom stream after class the other day. Try the assignment, try the quiz. If you haven't got to the quiz yet after like 45 minutes of effort, maybe you didn't do notes, or maybe you're really struggling with the math, but after 45 minutes of effort, please start on the quiz. All right? You can do your retake after you get some more help from me, but I need to know where everybody's at before a class starts. Okay? If it's 2 people behind, if it's 20 people behind, I need to know which situation I'm dealing with, and I'd like to before I start class. So that's why I'm asking you, please take the quiz. Next, the lab. It's called the PhET Lab, Finding Capital G. And we're going to recreate the experiment that Lord Cavendish did to figure out what capital G was. Isaac Newton knew the 3 parts of the universal gravitation equation, but he didn't know capital G, and he couldn't figure out a way to get it. So you're going to go into the assignment. You're going to see there's 3 directions. Read the first 2 pages. Follow the directions of the procedure. Collect data. Calculate capital G for each trial. And then answer the questions on the last page. Submit the assignment. This is what I would like spend another hour. All right. So it's in class time. You spend an hour, maybe less if you prepared, but no more than an hour to get up and through the quiz, and then another hour working on this lab over 2 days. Okay. So you have more than an hour during our class time, which you're all watching this for, and then you make that other hour before class Thursday to be ready for this. Anyway, so we have this Google document. I'm going to open it with Google Docs. It'll be easier to type and read into, but feel free to download or do whatever you got to do. And the other link here opens up the simulation. So it looks like this. You should just be able to hit the play button. It should work on everything. It probably even works on phones, although I would try and do a Chromebook or a laptop with this. So that's the simulation. Reading these directions, this is just a little bit of history about Isaac Newton and this gravitational stuff. Mr. Swift wrote it. It's a cool dude. Henry Cavendish, scientist who figured this stuff out in the early 1700s. And again, he figured out a method of measuring how these 2 balls were attracted to each other with this very, very delicate, precise balancing apparatus. I would say, if you're curious, I'm sure you could find a YouTube or 2 about how that experiment worked. Okay? But for us, once we've read these 2 pages of history and background, here's the directions for actual data collection. And there you can see a picture of the gravity force lab. There's a link if you didn't follow it before. Take some time and familiarize yourself with the simulation. Notice how force changes as mass changes and as distance changes. Okay, so if I just... Oh, I get sound. Are you getting the sound? Yeah. You don't have to have the sound if you don't want the sound. There's the sound, the no sound button. Okay, and here's a button if you were wondering how to do things with the keyboard. There's that button too. Anyway, notice how if I move them farther apart, the force gets weaker. If they get closer, the force gets stronger. Okay, and also notice that we can change the mass, and by changing one object's mass, we change the force of gravity between both of them, right? Because the blue ball pulling on the red ball, that force has an equal and opposite reaction of the red ball getting pulled back by the blue ball. All right, and if you want to type numbers in, you can't, but if you want to just change one at a time, you can click. So that's how we use the simulation. Fill out the chart below for various objects at various distances. Don't use the same masses twice. Don't use the same distances twice. Okay, cool. We can do this. So let me just go over, and you know what? Maybe I will split screen this. Alrighty. So let me get this all organized nicely for some split screenage. Apologies for the impatient among you. What if we cut off that last column of calculation? That's fine. So I have, there's a column for calculating G at the end of this, but I'll go through an example. Um, so the mass of object one, 441. Cool. Massive object number two I have is 400. And the distance between them, notice you can drag this ruler around, so I'm just going to put a 0 right on here. It seems to be 2.6 meters. Each of those marks seems to be 0.2 meters. So 1 meter, 2 meters, 2.6 meters. Okay, and the force is 0.000001741,579. All right. So those are my numbers. And now to do this again, I would just change the masses, the forces. I would write down these new numbers, okay? I would still have the same, do the same thing, but you fill in the other five. It's just 5 random masses, or 10, 5 random masses for the other object, 5 random distances. Just no repeats, okay? Just mix it up. And then write down the force that goes with each. Oh, look, they'll do scientific notation if you want. That's cool. I'm going to leave it like this. So that was step 3. Step 4, solve for the universal gravitation constant, G, and then compare it to published values. Okay, I'm coming back to the notebook paper now. See how much that covers. Ooh. Break that bad boy down a little bit. Yeah, all right. I dig that. This is simultaneously the most technologically advanced screen share and also the lowest production value. Alrighty, where are we at with time? Oh my goodness, 16 minutes. Okay, let's get this moving. So, this is my gravity equation most of the time. Capital G m1 times m2 over distance squared. But I want the capital G all by itself. So what do? I'm going to multiply both sides of this equation by d squared. I'm going to divide both sides of this equation by m1 and m2. And by doing that, the m1s and the m2s cancel. The d's cancel. Don't ask what. And that's my solution for capital G. D squared times the force of gravity divided by mass 1 divided by mass 2. Okay, and you can take this to the bank and use it for all 5 calculations. You don't have to do this algebra again. If I skipped steps, don't sweat it. Okay, this video is getting long enough, and if you use this formula, d squared times fg over m1 and times m2, you're gonna be fine. Let me put in my numbers. Well, let me write down the numbers I want to put in first. D was 2.6 squared. The force of gravity was point. I guess I won't have to do scientific notation for this one. There was 5 zeros and then 1, 7, 4, 1, 5, 7, 9. All right. And then on the bottom, we had their 2 masses. Mass 1 was 660. Oh, no. I'm sorry. Let me work off my data table. Sorry, I'm reading the screen, not the data table. So mass 1 was 441. And mass 2 was 400. Okay, and there's no squaring here because remember, distance is what's squared, and that was what was on top of the equation. So I'm just going to throw all this mess into calculator again. And then we'll be all set. All right, so let's clear all that. 2.6 raised up to the second power times 0.000001741,579 divided by, and I'm putting the whole bottom in parentheses again because order of operations. If you don't know why, well, ask me later. 441 times 400, that's m1 times m2, close the parentheses. Alrighty. 6.674 times 10 to the negative 11th power. Oh, you didn't see any of that because I left my screen open. Or left my notebook open. Okay, well, anyway. Why is that? I don't even know what I'm grabbing. Alrighty. Anyway, so I put those numbers in. Sorry to cover it up with the notebook, but it calculated out to 6.674. So that's what I'm going to write. 6.6740 times 10. Actually, I should say E. We can just go capital E or little e. Yeah, it does really. Whatever. Negative 11. That was my answer. And I'm going to go through and I'm going to take the other sets of data, the other four numbers, and redo that calculation again and again and again to calculate capital G all 5 times. And then whatever the average is, that's your predicted value of G. Let me move my head so that makes some more sense. Down here, you need to put your predicted value of G. That's the average of the five G's from your 5 trials, the 5 times you wrote down data. And then the last section is questions. Gravitational force is always, well, you should know. Okay. And I think these are good review type questions. Hit on some of the same stuff, excuse me, as what was in the lesson. So we are at 22 minutes, and yeah, here's a few more problems to practice if you did not have a chance, and then we're wrapped up. Okay. If this takes more than an hour, stop. I don't know if I want you to turn it in, but at least stop and like either come to class and explain why why you stopped. All right, like I was doing it for an hour, Mr. James. I didn't get stuck on anything. There just wasn't enough time. Or maybe it's like, Mr. James, I got stuck on this one thing for 30 minutes, and you said stop after an hour. That's fine too. Okay, but yeah, this video is already it's pushing more than 20 minutes, and that's like 20 minutes less of it's 20 minutes less of working time. Okay, so anyway, if we check the weekly overview, we've previewed the assignment. We were planning to work together. You are still welcome to arrange to work together with other people from the class. When we get back Friday, we'll talk about powering up, what that means. Oh, I'm sorry, Thursday. When we get back Thursday, we'll talk about power up. It's going to be a new class feature. It's kind of a way for me to explain some things that maybe other teachers don't explain about, how to like just be good at adulting. We'll check in on the FET lab, see where we're at, and then whatever time we have left on Thursday, I'll introduce Coulomb's law, which is the rule for how electricity works, which has this beautiful, amazing symmetry with the way gravity works, and that's why we're going to look at the electric force equation in the middle or in the beginning of our gravity force unit. I hope this is helpful. Again, once you've maxed out 2 hours between now and next class, like, feel free, grant yourself some chill time. Okay? Stay strong. I'll see you all on Thursday. Peace.